Good evening, ladies and gentlemen. I am so ridiculously happy to be here and to speak to you tonight about something that interests, I hope, all of us, namely the concept of light. Right? The fact that we are able right now to see each other in this room is, of course, because light exists. Right? There's light, comes from all the way up in the ceiling lamps, it beams down, it bounces on my body, gets into your eye, and you are able to see me as I am able to see you now. Now, the bigger question, however, is why does light exist to begin with? And in order to answer that question, we have to look at a couple of properties of light tonight, and that's my job, so I'm very happy to take you on a journey to first discuss exactly what do we mean by light, and then hopefully answer the question, why should light be there at all? Now, let's talk about light just for a moment more. Clearly light exists. Again, we can see each other. Now, this is because light, of course, comes from the lamps, and if you go outside, it might come from the sun. But if you go in outer space, space happens to be pitch black, right? And it gives you the impression that, well, in outer space, there's not that much light floating about. But there is. If you are able to take a photograph of what outer space looks like, it actually looks like this. This is a sky map, right? If you were to take a picture of the universe, and people can do that with their satellites, this is from the Planck satellite, then this is what the universe looks like. Clearly, it is not pitch black. In fact, it's, well, more red than it is black. And that is because the universe consists of, well, red light. It's very ancient, very red light, very old, and you're not able to see it with the human eye. The human eye is simply not sensitive to it. It's too red for the human eye to see. This is why we need a satellite like this to pick it up. So we know that the universe is doused in light. My question tonight is not so much where does this particular light come from. By the way, it's called the cosmic microwave background for people who want to look into it. That is a whole lecture by itself. But again, my question is a deeper one. Could the universe have existed without light, this or any other? What would the universe look like? Well, first of all, it wouldn't look like anything because you need light to look at things, okay? But that's not exactly what I mean. Clearly, if you take away the light from the universe, things might look different, they might behave different. But my question is still deeper. If we were to build a universe and we would not put light in it, could the laws of physics have existed at all? Could reality have existed? The answer, surprisingly, is no. So that makes light a very special thing in the universe. It's not just something that makes us able to look at the universe and make sure that things are connected in different ways. It makes sure that reality can exist at all. Well, that's my job for tonight. So let's talk about physics for a little bit. So if you were to talk about physics, there you go. Then there's all kinds of different fields of physics, right? All of these, by the way, are a complete Royal Institution lecture by itself. For instance, you have celestial mechanics up in the lower left corner. This is how planets and stars and gravity behave. You can look at something more, well, deep and mysterious, like quantum physics on the right-hand side. On the left-hand side, you have these beautiful steam engines that you can see here in the museums in London. And the lower part is gravitational wave physics. That happens to be my particular field. And here's the thing. Nature has all these different parts of physics that have their own laws and their own rules, and they've all been figured out, most of them, still work to be done, and they all work individually. But if things work individually, it doesn't mean necessarily that they work well together. And that might be a problem, that you have one field of physics that says, these are my rules. And you have another field of physics that says, no, but these are my rules, and the rules work individually, but they sort of get into trouble with each other. It's sort of like two people having a row, yes? Take two people who don't like each other very much and put them in the same room. Here's somebody with their own sets of rules, so and so, and here's somebody else with their own sets of rules. but they don't like each other very much. What you then need is a third person to come in and smoothen out their differences. This is light. That's going to be what we're going to see tonight. We're going to have different parts of physics that like each other, not so much. And light has to exist to make sure that they do. So in that sense, light is a necessary ingredient of the universe because otherwise individual parts don't like each other very much. So what are the individual parts? Well, here they are. Okay? There's two ones in particular that we have to make sure that like to get along a little better. One of them is up in the left corner, up there. Nature has a universal speed limit. That's a rule of physics. There's a particular velocity in nature that you cannot go faster than. Some of you might know, oh yeah, I know that number. It's the speed of light. I agree. But it's not trivial that that number exists, that there is a maximum speed number. And just to be clear what I mean by that, I mean that if you try to go faster than this particular velocity, nature is going to stop you from doing it. Nature really doesn't like you to go faster than that particular number. That number, by the way, is 300,000 kilometers per second, right? That's a huge number. That means if I were to take something that goes with that velocity, let's take light, and let's make it so that I shoot a beam of that stuff up until the moon, it gets there in about 1 second. That's how fast it goes. It's a very high velocity, so don't worry, you won't get any speed tickets if you're going to go faster than that number. It's going to be very difficult to do so. But that's one of the rules of physics that nature really wants to adhere to. There's another one. Nature loves to have symmetries. Now, what I mean by symmetry, we will see in due course of tonight. Okay? Now, here's the thing. Those two don't like each other very much. And this is where something has to step in to smoothen out the difference. And that thing, as we will see, is light. So the fact that nature wants these two guys to play along means light is a necessary ingredient. This might be a little abstract at this point. So let me give a quick example. Yes? Suppose that I were to take a nice pot of tea here. Okay? And it just comes out of the kettle. Then this is about 80-ish degrees or so, right? Scorch my lips if I try to drink it. Yeah, and that's a sucky thing. That's not symmetric. Why? Because my body happens to be 37 degrees. The cup of tea is about 80. That's an asymmetry. The numbers are not the same. So nature says, yeah, I don't like that asymmetry very much. I want your lips or the room to be the same temperature as my cup of tea. Now, of course, you all know this because if you put a cup of tea over here, at some point the room and the cup of tea will have the same temperature. It will smoothen itself out. Yes? This is nature's trick to try to make everything be the same. Get a symmetry back. In this case, it would be a temperature symmetry. Now, as you also know from putting a cup over here, that cooling down doesn't happen in 0 seconds. It takes a while. Might take a few minutes, might take a few hours. That is that rule over there. Nature doesn't like whatever it needs to get the cup of tea be the same temperature as the room to happen in 0 seconds. There's a speed limit that says, no. You have to wait your turn. You have to make it slower than that particular velocity. Now, that means that something has to come in to make the cup of tea be the same temperature as the room. Something has to travel from the cup of tea into the room to smoothen out the asymmetry in temperature. Yes? Now, if this is a little abstract, think about me. I'm from the Netherlands. As you can tell from my accent, I'm sure. I'm from the I wish I had your accent. You have a beautiful accent over here. I'm from the Netherlands, okay? So if I want to come to London and this speed limit says, yeah, but you cannot do it in 0 seconds, then you know immediately, just from the fact that I'm standing over here, that something took me from the Netherlands to here. Be it a car, maybe it was a plane, maybe it was a train, maybe it was my own 2 feet. But the fact that I could not teleport in 0 seconds, that I had to use that speed limit, tells you something, namely that there must have been something that got me from A to B. Well, that thing, in my case, was not my 2 feet, it was actually the train. But you know that that thing exists. That's what we're going to do here too. That's the same thing with my cup of tea. Something traveled from the cup into the room to get the symmetry right, at the same time adhering to the universal speed limit. In case of the T, that thing is what we call heat. It's an energy. Fine. But we will see that there's other symmetries in nature that also give you something that has to travel, and that thing, as we will see, is light. Exactly because these two things don't like each other. Light has to step in to make the traveling go, not in 0 seconds, but in a bigger amount of seconds. That's the plan for tonight. Now, before I go into more detail, I think it would be a good idea if we talk a little bit more about what light is exactly. Right? And then we can go into these details, and then we can see that light will come out. All right, so we're going to do a little bit of a history lesson. What is light to begin with? Now, that's an interesting thing because light is actually one of the things that was mostly discovered by people working here at the Royal Institution about 150 years ago. There's many people, by the way. This is a field that many people worked on, but some of the people, including Michael Faraday, worked right here at the Royal Institution, and they were investigating something that itself was not light. They were investigating different things. They were investigating, on the one hand, this thing called electricity. On the other hand, they were investigating something that's called magnetism. To us, these are relatively well-known concepts, right? You put something into the socket and your light bulb will go on. So we're sort of used to electricity in every day. We're also used to magnets. We use it to put our grocery lists on our refrigerator door. We're sort of used to these two concepts. But to those scientists, 150 years ago, a little bit more, those are completely new phenomena. And when they were investigating electricity and magnetism, they sort of accidentally found light. So let's go through that history lesson for a moment. Here's some mathematics. Now, don't worry, it's not a mathematics lesson. For the people who are in the know, these are the famous Maxwell equations. Many scientists work on this, including Michael Faraday. James Clerk Maxwell over there was the person who put everything, all the discoveries, into one big cohesive mathematical framework they now are called the Maxwell equations. Now, we're not going to make it a lesson on mathematics, we're just going to demonstrate both. Let's start with electricity first. So, electricity, I can actually demonstrate with this thingy over here. I was shocked a few times today when I was sort of setting up this thing, okay? I was wearing a different sweater, the type that attracts electricity, so I got a couple of 100 volts through me earlier today. Let's see if I can do this without this time. I changed shirt in the meantime. Okay, so what we have is what is called the Van de Graaff generator. And without going into full detail how it works, what it does is it takes these two metallic spheres, fills one of them up with charged particles, electrons, fills the other one up with other charged particles, the opposite charge, and pluses and minuses like to get together. If the distance is small enough, they can actually make the jump. You will get a nice surprise there. So let's actually make that work. Virgil. There we go. Oh, you see that? If I'm evil, I'm blaming Virgil now, right? He came here and I got a shock. Okay, so what these two spheres are now doing, by this generator out, that's the second one. It's like I'm doing this on purpose. I'm not, okay? So you have these two spheres, they're all both being charged up by the machinery over here. And if you get them close to each other, thanks Arnold, then clearly you can see the jumps of the particles happening. Everybody seen this? Yeah? Okay, now I don't dare to touch them anymore, so I'll try to do it over there. And then let's decharge them. There you go, one final spark. The house lights can go back up again. Thanks, Arnold. So, this was electricity. And people were figuring out how that works. And, well, this is what they found. You can actually apparently make pluses and minuses come together. And this is what we call in these formulas over there, that's the capital E number. It's called the electric field. Okay. Forget about the electric fields for a moment. Let's look at the other field. Magnets. That too was something that was investigated by people 150, 200 years ago because they noticed that some metals really like to attract some other metals. For instance, these two, there we go, like to attract each other. There you go, right? I'm not showing you something you didn't know. Magnets exist. Here too was something that people were investigating, and that is called B, because magnetic fields obviously start with the letter B. That was for reasons of history. I wasn't there when they did it, but they decided to call magnetic fields by the letter B. Now, here's the point that I'm making. They were investigating these two phenomena individually, and they found that the electric fields are given on the left-hand side, magnetic fields are given on the right-hand side. So far, so good. But if you now look at the other side of the equations, there on the right-hand side, you see two new equations. Again, ignore the details of the mathematics, just notice one thing. Both of these equations on the right-hand side have both an E and a B in it. Mathematically speaking, that means electric fields and magnetic fields are not independent thingies, they are related. And this was a big discovery, again, amongst other places done here at the Royal Institution, that apparently you can turn electric fields into magnetic fields, you can turn electricity into magnetism, and magnetism into electricity. So, let's do a little experiment of that as well. Let's take, for instance, here a nice compass. Yes? Okay. So a compass, as you know, wants to point towards the north. And if I put the compass here, Arnold, can I have this view over there? Thank you. Then what you can see here, well, it tries to follow the magnetic field of the Earth. The Earth is one big magnet. I mean, it has a small strength, so you don't particularly feel it, but the effect is there. That's why compass needles move towards, there you go, towards the north, right? That's how old people in ships knew where to go. And over here, I have a piece of electricity. It's a wire that contains charged particles, just as we had in a generator over there. But these charged particles have an electric field. Now note that the compass really doesn't care about the presence of electricity. You notice that? Doesn't move at all? But now I'm going to do the following. It's a famous experiment done by Oersted, a Danish scientist. He hooked up the wire to a battery. If you do that, then lo and behold, give me a second to hook this guy up. And there you go. There you go. You see that? Every time that you see the compass needle move, it's when I attach the other side of my wire to the battery. Here's something interesting that happens. When I put electricity next to the compass, the wire itself, nothing happened. The magnet did not care at all. But at the moment that I actually made the particles in my wire walk about, because that's what you do. If you attach it to a battery, particles in the wire walking about, and all of a sudden, my compass knows about this. Apparently what I've done is I've turned electricity into a magnet. Right? We would now in present day call this an electromagnet. To us this is well known. To them this was a complete surprise. Apparently electric fields do not feel compasses unless you make the electric field move about. That's interesting. But then you can immediately ask yourself the question, does it also work the other way around? I've now turned electricity into a magnet. Can I also turn a magnet into electricity? Okay, so people went on experimenting, and we can actually demonstrate that that works as well. Look what I have here. Here's a light bulb. It is off. What I have here, it's built into this little contraption over here. What you have over here is actually a magnet. It's built into this thing. And note, the fact that there's a magnet there does not give me any electricity. But before, we could make a magnet if we made electricity walk about. So what if we make the magnet walk about? Will that then produce electricity? And sir, can I ask you to be a volunteer? Can I ask you, what is your, do you know your lung capacity by any chance? This is something that you have on the mind? Well, I actually don't know. We'll just figure it out. No, what I'm going to ask of you is whether you can blow on this little mill here, yes? And if it turns about, then the magnet will wobble. And if the magnet wobbles, then you have something, you have a moving magnetic field. And if, well, nature is in any way symmetric, you would expect then maybe this light to go on. So if you can just give it a little blow. Oh. Ah, there we go. Apparently, the answer is yes. Just as you can, if you wobble about electricity, as we did over here, you get a magnet. And if you wobble about a magnet, as the gentleman did over here, you're going to get electricity. Let's see if we can make the effect a little stronger still. This has nothing to do with your lung capacity. You have to blow hard to make it work. So can I ask you maybe to hold it up for just a bit? Maybe you can hold up so everybody can see this. Okay, and maybe you can just point in this way, because I might want to blow into it. But you know what? My lung capacity is not very big either. But this guy's lung capacity is pretty big, okay? So let's see what happens if we're actually going to make the effect a little stronger still. So let me plug this guy in. All the way over here. Let's see if it works first. Seems to be okay. All right. Arnold, can we have the house lights go down for just a bit? Thank you. Ah, okay, there we go. There's a nice little piece of light there. Can I have an applause for my two volunteers? So thank you very much. Thank you. Now, these experiments, again, were already done. We're still in our history lesson here. These experiments were done already some time ago. Let's talk about light now, okay? Because we were discussing how people found out what light was to begin with. Clearly, people knew what light was because people have been looking at it, people have been measuring, people had actually measured the speed of light. That was that number, 300,000 kilometers per second. But these people, like Maxwell and their friends, were not investigating any light. They're investigating magnets and electricity and whatever relationship that they have, and this happened to be the result. Now, again, ignore the mathematics. Just remember, wobbling the one gives the other. And then Maxwell, the scientist, this one, asked himself the following question. Wait a minute, doesn't that mean that if I wobble this magnet about, I should get electricity? We just saw it demonstrated. So, right, I wobble this, I get electricity, but electricity itself, if it wobbles, well, just like the compass, you get back magnetism. But if magnetism wobbles yet again, you get back electricity. And it goes back and forth and back and forth and back and forth. The experiments that we just did showed that this is in principle possible. You can now ask this question then, well, okay, well, does this wobbling back and forth, does it stay in one place? Or does it itself move through space? Does it go from A to B? And Maxwell took these equations and he figured it out, right? He had to play with the mathematics a little bit, and then he actually found the following. This is an animation. He found that if you wobble the electric field, that's in blue, then it makes magnetic fields, that's in red, and they change back into electric, back, forth, and that indeed travels through this room from A to B. And his formulas even told Maxwell how high a velocity this back and forth traveling had. And the number that he found was 300,000 kilometers per second. That was the speed of light that people had already measured in completely different ways without knowing electricity and magnetism. That was an enormously big discovery. So Maxwell himself, the scientist, said in nice archaic English, and I'm not a native speaker, so you might have to help me out here a little bit. We can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electromagnetic phenomena. Okay, let's translate that in normal plain English, okay? It says I have discovered that light is just a wobbling of electromagnetism. That's what it says. Now, there were no Nobel Prizes back in those days. We're talking about 1860s or so, but he clearly would have gotten it. He had discovered what light was all along. Now, that is a very, very big discovery. Okay, so that is our history lesson. So we have an understanding of light now. Now, again, I don't want you to understand these equations in full, but do make a little mental snapshot of what they look like. Okay, let's speak again. There you go. All right, everybody got the snapshot? Yeah? Okay, good. All right. We're now going to see whether this electromagnetism is a necessary ingredient of the universe, right? That was our original question of this evening. And if you now notice, by having this little detour into history, I sort of, made the question bigger. The original question was, could the universe have existed without light? Now we know that light is just the transverse undulations of electromagnetic phenomena, so on and so forth, the wobbling of electromagnetic fields. The question now is, okay, could you have made a universe without electromagnetic fields? And as a consequence, would you have had light? That is now the bigger question we're going to answer. And as I promised at the beginning, we're going to have two rules fighting with each other, and this electromagnetism has to come here and clean up the tension between two thingies. Yes? So, we're going to build a universe. We're going to start with the universe, no electromagnetism at all. No electric fields, no magnetic fields. We're going to have some space and time in there. Right? We have a universe with some space, time flows. We're going to put some particles in there. Doesn't even matter what kind of particles, electrons, protons, take your pick, just put some particles in there. Yes, you need stuff in the universe. Okay. In my story right now, I'm going to first look at the first rule, that nature has a universal speed limit. Yes? It is the speed of light. We don't know it yet because we don't have light in our story yet. But I'm going to show you that there must exist a universal speed limit. Then we're going to talk about, okay, but what's that second ingredient? The existence of symmetries. And again, I will explain to you what those things are when we get there. And it's those two things, if you recall, they're going to fight with each other unless electromagnetism jumps in to smoothen out the difference. That is going to give us a rule about the existence of special particles. Those are not light particles yet, maybe the photons. Electromagnetism, you can also see small particles of light floating about called the photons. But we will see that to make the tension go away, we're going to need new particles. And then the only question remaining is, okay, of all particles we will need, are those photons? Are those the photons that make up electromagnetism? And in order to get that, we're going to sprinkle over our small universe a small amount of quantum mechanics. And then, once we have done that, we will have light. All right. So, let's look at all the ingredients a piece. First ingredient was, we're going to need a universal speed limit. At this point, some people already somewhat in the know in physics. In fact, there's an individual over there that is one of my former students. Hi, Andreas. Nice to see you. So I'm sure he knows the answer. And some people might as well, yes, because indeed, the universal speed limit, this velocity you cannot go faster than, is the speed of light. But remember, we don't know it yet. We don't know about light. So I'm going to have to get this universal speed limit for someplace else. So that is what I'm going to discuss with you now. So I have to get it from some other part of physics. You can actually get it from balloon physics. Don't laugh at me, okay? I'm standing here with my balloon. I'm a middle-aged man holding a balloon in the center of London. But there is a point to this. Now, we know that the balloon in this particular case is filled with helium. Helium has this nice property. It's a special gas. It's named after the sun because people investigated it, that there must be some special gas. And the first place they found it was in the sun, so they named it after the sun god Helios. So that's why it's called helium. Helium wants to go up because it's lighter than air. It wants to float on air. Helium is in that balloon. In the rest of the room, there's just normal air. Particles. Particles flying about, bouncing about. Let's also pretend we don't even know about the particles either in the balloon or in the room. even without knowing anything about the particles here or in the balloon, there's one thing I can immediately conclude about whatever's going on in the balloon and whatever's going on outside of the balloon. The in and the outside of the balloon must share some number that is equal to each other. How do I know this? Because the balloon is not changing. It's not changing shape. Now, I don't dare to let it go. Fergal, would you mind holding it for a moment? Here's another man holding a balloon in the middle of London. This is not a triviality. The fact that this balloon is not changing shape, it's not getting bigger or smaller. I mean, I can easily make a balloon make its shape become bigger or smaller. Here, look at this. So what I did there, I put on a vacuum pump. It just sucked out a little air from the little container over there, and that means the particles on the inside are bouncing a little stronger, pushing the balloon out, than the particles on the outside are pushing in, because I've removed the particles from the outside a little bit. Then the balloon is now getting bigger, and as it was changing, this is when the change of the balloon happened. When I changed the inside of the container, the balloon also changed. It stopped changing now, agreed? So that means, well, whatever is going on in the balloon now, it is again has turned into the same number as outside of that balloon. Now, if you know about your bouncing particles, then you know that that same number is simply called the air pressure. But even if you had not known anything about bouncing particles in the air, just the fact that inside and outside at some point do not change anymore is another way of saying there must be a shared number between inside and outside. Even if you don't know anything about particles, we do because we live in a modern age, but just the fact that it doesn't change anymore. And I can make it stronger still, because here's another balloon. I have no idea whether there's helium in there. You're sure it wants to go up, but other gases do too. So I don't even know what this balloon is filled with. But yet again, I know exactly that there is a number that is shared between this balloon inside and the outside world. Slightly stronger still, I even know that whatever the number is, must also be the same number between the two balloons. Now, this all sounds very trivial, but there's a very deep rule that's going on over here. The rule that I'm talking about is this one. There's a rule. Very abstract. If there's two thingies in nature, for instance, the two balloons, A and B, and they agree on C, C being now the rest of the room, then there must exist a number that is the same in between those two balloons and the rest of the room. Again, we know that number because we know about bouncing particles, but that number is what we call air pressure. But even if we didn't, we wouldn't be able to conclude that that number exists. Yes? Now remember this rule, because this rule applies at many places in physics. In fact, I'm going to demonstrate yet another one right now, and once you've grappled with this rule, then we can find that there must exist yet another number that is shared with all, and that's going to be the speed of light. So, let's see, I have a nice ring here. Let's see if I can give somebody a ring. Well, here's a person. Would you mind giving, if I gave you a ring? Do you have any significant other around that might beat me up later? I hope not. This is all for science, okay? Just put the ring on one of your fingers if you can. Can you tell me what color it is now? It's a green one. Okay. Does it stay green though? Okay. Start off with green. It's getting purple-blue. Something is changing. That meant when you put the ring on, some number between you and the ring was not the same yet. And nature is now trying to make those two numbers the same. Yes? I can do better still. I also have two of these. Oh. It's also a gravity experiment that I'm showing you now. No, I just dropped the thing. I have another two of these rings right here. By the way, these are called mood rings. You might know them. A few decades ago, this was sort of a fad in the world. And apparently, the color of the ring tells you what mood you're in right now. So, what is yours at this moment? multicolored? What's the dominant one? Purple. When I bought it, they gave me an actual legend that tells me how you're feeling right now. Extreme trepidation, is that close to what you're feeling? It actually says romantic. So I have two of these. I also brought two of these rings, and I put them on my finger, and they too are changing. Yes, changing their color. Now, if you give it a little while, because it takes a while, remember, it takes a while for things to find their new equilibrium together, then note mine, do you see that? Are also becoming greenish, so and so. Now, what does it tell you, given this rule that you have on the board now, about those two rings, ring A and ring B? Apparently they agree on something, namely C, that's me. Okay? Oh, they do, because they have found the same color. By the way, what's yours now? Very multicolored. So you're going through a whole range of sentiments now. Okay. I'll try not to. Yeah, thank you very much. Can I have an applause, by the way, for just getting my ring there. What does it tell? I mean, but let's focus on me and my two rings, yes? One ring, A, the other ring, B, attached to me, C. And the two rings apparently are in agreement about me because they turn the same color. What does it say about me and the two rings? There's something that is the same. Yes? Some number must be the same. In this particular case, indeed, that number is the temperature. Yes? It doesn't quite, as far as I can tell, I was joking a little bit there, it doesn't quite react to your sentiment. What it reacts to is your temperature. So if we keep up these rings long enough, they should all get the same color because human beings tend to have the same temperature. But here too, even if we had not been able to ourselves feel with our body's temperature, and thermometers did not exist, we would be able to tell some number is shared between all of us in those rings. That's again an application of this rule. Okay, but we were planning to talk about the existence of a speed limit, a bigger speed limit. Okay, let's make it a little bit more abstract still. There is a highest velocity in nature. Yes, it's the speed of light. And when Einstein, who sort of brought up this number, he found it by looking at electromagnetism. But that's not the route that we're taking because we have a universe that doesn't have electromagnetism in it at all. Okay? So, but we do have a new rule. We have that if A and B agree on C, then there must exist some shared number. Now, can I take you as an example, just for a second? Can I ask you what is your favorite vegetable? Potato. I'm more of a broccoli person myself, but potato is good. Yes? If I ask you what your favorite vegetable is, you say potato. Now suppose, I'm not going to ask somebody on stage, but suppose somebody would have come on stage and that person is walking with respect to the gentleman over here. That means that person and myself are not the same person, right? We have a velocity with respect to each other. If that person would now ask the gentleman over here his favorite vegetable, I think we can all agree that you will still say it's potato, right? And that is, of course, because there's nothing about you and your favorite vegetables that's going to change simply because this person and my hypothetical other person are moving with respect to you. Let's do this in terms of this rule again. By the way, this is called the principle of relativity, that nature, that will be you in this case, is completely indifferent to whether you're looking at it from a velocity or looking at it from a stationary position as I am right now. Your love for potatoes has nothing to do with doing this or doing that. That's what we call the principle of relativity. But wait a minute, that means that there is now a person A, that's me. There's a person B, that was the walking person, agreeing on person C. Then this rule says that we just found that there must exist a shared number. That number is not temperature. that number is also not air pressure. That number is a velocity. There's a number that all of us agree on, no matter how fast we are moving. That number is itself a velocity. So from this little thought experiment, you can derive the existence of a number, a special velocity that's the same to everybody. That number is, well, a special velocity. By the way, you can actually turn this into mathematics. So for the people maybe who want to actually see this, everything that I've now been saying into a mathematical structure, you can go over there. Right now, I hope the message is clear. A and B agree on C, then there must exist a shared number. In this particular case, that number is itself a velocity. By the way, it's a velocity because this person, myself, and the new person, also asking you your favorite vegetable, themselves differ by a velocity, agreed? Okay, but that means that shared number must sort of mop up the difference between those two velocities. That makes the shared number a velocity. And as a final step to this argument, we just have to put in that a shared velocity must also be a highest velocity. Remember, that was the speed limit we were looking for. Now, how do you figure? How is the fact that we all agree on a particular velocity mean that it's also the highest velocity? It's actually not that difficult. Suppose that this special velocity, let's call it c. Yes? Yes. In physics, that is the speed of light, but I'm not assigning a number to it. I'm not saying who goes with this velocity, simply saying that it exists. Okay, if that velocity exists, and suppose that I'm going with that velocity, and if I can take these two gentlemen, you just have to sit tight, you don't have to do anything, but it's just you two as an example. If I go with this velocity, and both of you will have to agree that I go with that velocity because that's what it means when you have a shared number. Suppose that it is not the highest velocity. That means if you come running after me, then you should at least, because you can go faster than me, you should at least be able to go along with me, yes? But what is the velocity between you and me if you're running along with me? How much velocity do we have with respect to each other? That's 0. But wait a minute, the gentleman over there, who is not walking along, says, no. I get whatever the number c is, 300,000 kilometers per second, but we should share the numbers with each other. You cannot have this rule that it should be the same number, and at the same time somebody is saying it's 0, on the other hand somebody is saying it is a different number. So that means my premise that you are able to walk along with me is flawed. By saying that it's not the highest velocity, I'm able to construct a situation where this is broken. That you do not agree anymore on that this is our highest velocity, or that's the same velocity. That means it must be the highest velocity. This argument too is worked out in more mathematics over there. But the point that I'm making here is, apparently there exists a velocity in nature that is the highest and is shared with everybody. And I didn't get it from electromagnetism, I got it from different means. I got it from this special ABC rule, so to say. Yes? Now, if you read into the history books, people usually get the number from Einstein or electromagnetism, but remember, we're building a universe without electromagnetism. So fortunately, we got it from someplace else. Okay, good. Then let's move on to our second ingredient, symmetries. Remember, there are two rules that don't like each other very much. One of them is the universal speed limit. We have that one. The other one is symmetries. So let's talk about what we mean by the word symmetry. And I'm going to use this drill over here. Now, as you can see, it's a wheel attached to it and there's all kinds of different colors on it. Actually, can I ask you, sir, which colors can you see on it?
Red, purple, orange, green, mauve, yellow, blue.
It's a hodgepodge of different colors, yes? Okay. Now, if I'm going to spin this wheel around, can you tell me again what it is that you're seeing? Yellowish?
Yellowish.
Yellowish, exactly. It sort of blurs together into one color. Now, if you would really have all colors combined together and you would then spin it around, it would become more white. But to my point, it's just the fact that it becomes yellow. Okay. If I can go to the lady over there, can you tell me which colors you can see on this wheel? Different wheel.
Purple, blue, green, yellow, orange, red, and different purple.
Different purple, okay. It is actually the same set of colors as that wheel has over there. Okay, and I'm going to spin it again. What is the net color?
Probably more beige.
Yes. Again, it blurs together. Now, those two colors are pretty, so the blurred image, so to say, is pretty similar, right? Now, here's an interesting thing, though. When I was spinning these things around, they sort of blur together into very similar colors. But do you see any difference between the two wheels? I hear people say yes. I see people squinting their eyes and see people sort of, no, I'm not quite seeing it. They're different ordered. Same set of colors, as the lady pointed out and the gentleman pointed out. When spinning, blurs into pretty much the same color, yet the order is different. This is what we call in physics a symmetry. That you can swap around colors in this particular example, yet the net effect is exactly the same. There's a freedom, so to say, to swap around colors. Yes? That's what we call a symmetry. And nature loves these symmetries. It's full of them. There's an enormous amount. Here's another one. Here's a little ball. Note there's a little wave on top of it. And if I just turn it a little bit, it looks pretty much the same still, right? Still wave, so you can sort of turn this around and the whole thing doesn't quite look any different. That too is a symmetry. And nature is full of them. Nature loves these symmetries. And these symmetries mean that, well, you should be able, if I stick to this example, to swap two colors around without seeing a difference, right? But wait a minute, then we run into trouble. This is where the tension appears between the two wheels. There's a small nuance. There's a thing called a local symmetry and a global symmetry. What I mean by local is that if I take one of these two wheels and I look at the colors, then yes, if it's not spinning and you look at it, you can actually tell it's not quite the same as the other one. You were all able to do this just a second ago. That's a local symmetry. As in, I'm able to swap the colors around on this wheel as long as I don't look at the other wheel, so I can see that the colors were swapped around. But there's also global symmetries. That means you can swap around the colors over here on this wheel, and the colors on that wheel should also change. Nature loves global symmetries, that if you swap around two thingies here, then at this part of the universe, then that part of the universe must also see those two thingies swapped around, because the net effect is the same. Here is where that tension that I was talking about at the beginning comes from. Because we have our two rules, nature loves symmetries and there's a highest velocity, here's the tension. The people over here take their color wheel. They swap around two colors. The people over there have their color wheel. But then all of a sudden, there is not a global symmetry anymore. Agreed? Because there's two colors swapped over here, but this part doesn't have their color swapped. And nature says, yeah, I cannot have that. I love my symmetries. I want the colors to be swapped everywhere. And nature says, I want this to be done as quickly as possible. But then that rule comes into play, says, wait a minute, if you want this to be done as quickly as possible, 0 seconds, that means something must have traveled faster than this highest velocity. And that is not allowed. So nature cannot have these two rules play at the same time. You cannot do swapping over here and have an immediate swapping over there to get the symmetry just right in all of the universe. The best nature can do is when something is swapped over here, is send some information from there to tell this part of the universe, hey, I just swapped something around. You better do it too. That thingy is a new type of particle. If you want these rules to play together, you're going to need new particles that send information from one side to the other. And that's the rule that you have over here. Every time that you have a symmetry, but at the same time, you cannot change things around and also have it changed around over there, something must have traveled to inform the other side of the universe that it happened. Those are special particles. In physics, let's use a complicated word, these are called gauge bosons. Special particles that make sure that those two rules play together. And because nature loves symmetries and has many of these symmetries built in, you're going to find many of these gauge bosons, many of these special information traveling particles that tells this part that something happened that that part needs to know about. In fact, here's a small list. For instance, if you take a particle in the center of an atom, like a proton. Protons themselves consist of smaller particles still called the quarks. There's always 3 of them. The proton doesn't quite care in which order the particles are in there, just like these wheels over there don't care about the order of colors. It just says, I need 3 quarks. You can swap them around at will. But it means if there's a proton over here where people swap around the quarks, then that part of the universe, because symmetry, needs to know about this, but it cannot happen in 0 seconds, something needs to travel. That special information particle in that case is called the gluon. And those particles not hypothetical, you can just measure them. Right? We measure them very often in our physics experiments. Here's another one. Protons and neutrons, also particles in the center of atoms. A proton is like a little ball with plus charge. In fact, it was the little particle that was in one of these 2 spheres over here, right? The one that makes a spark happen. Neutrons are pretty much the same particle. They don't have charge, but otherwise they weigh the same. They also consist of 3 quarks. But wait a minute, that means you can change protons and neutrons around, and nothing is going to change. If you take a nucleus, like a gold atom, and the inside is made of protons and neutrons, and you just flip all the protons and neutrons, you still have exactly the same gold atom. And again, if you do it over here, but nature wants their symmetry, it also has to happen over there, so something must travel from that side to the other side to say, hey, you have to also flip around the protons and the neutrons. Because you cannot do it in 0 seconds, because that breaks the universal speed limit. Now, that means there too must be a particle. That particle is called the meson. And again, those are completely measurable. These particles really exist. Now, we can move on and on. Big rule here is, if you have a symmetry in nature and you have a speed limit, there must exist a particle that sends information around. But there's many symmetries, and note that there's one thing missing from our list. It's the photon, the particle of light. And it turns out the photon is also one of those special particles that sends information from one side to the next. But as you now know, it does require you to know that there is a symmetry. There's a symmetry, something can be swapped around, yet you end up with exactly the same, requires a particle. And the question simply is, well, okay, but what is that thing? What is the thing? Which symmetry needs to have a photon to work in the whole of the universe? And this is my final ingredient. We need a sprinkle of quantum mechanics. Only a sprinkle. Quantum mechanics, we're not going to make it a quantum mechanics lecture. Just a small sprinkle, because we need to get our symmetry. What does quantum mechanics say? Quantum mechanics says if you look at very small particles, and you look closer and closer still, then every small particle is a little wavy. It does a little bit like this. Yes? That's what we have in my hand here. This is a particle, but there's a little wave attached to it. And the properties of this particle are represented by the properties of the wave. That's what quantum mechanics tells you. For instance, the wavy thing here has a certain amount of spread. How many meters does it take to go up and down? That is the mass of the particle. The more massive the particle is, the smaller the spread is, the more the waves are packed to each other. It also has an amplitude. How high does the wave go? How low does the wave go? That says, well, where is the particle to begin with? This is the only quantum mechanics that you're going to need to my story right now, because as I was demonstrating before, this wave, if you turn it about, question to the audience, has the spread of the wave changed simply because I turned my particle around? It hasn't. So that means the mass of the particle has stayed the same, even if I've rotated it. Second question, has the position, that was how high the wave go, has the position of the particle changed because I rotated it around? No, I mean, it's just the same particle or the same wave, just rotated around a little bit. That is a symmetry. You can take your particles and rotate their waves a little bit over here, but then if you rotate it, the particles over there need to know about it too. And because it cannot happen in 0 seconds, something must have traveled from this side to the other to tell the rest of the universe that this little rotation has happened. So, I'm over here with my particle. I'm rotating it, making the wave go around. The particle over here doesn't change, but that part of the universe doesn't know about it yet. So you guys are the yellow particles. Over here, there's the blue particles. And if I rotate this around and nature wants its symmetry back, it will have to send information over there because it cannot do it in 0 seconds. And lo and behold, there we go. The other guy will move along. It takes a while because it has to travel. That is that rule that you need over there. Right? That was what we found before. Those are two rules fighting with each other. And we found this beautiful list that if you have symmetries and information has to be sent around, you just have to look for the right symmetry to get the right particle back, the right gauge boson, as this is called. And in this particular case, the symmetry that we're looking for is the freedom, so to say, to flip around particles in quantum mechanics. And lo and behold, if you take that and actually put it into mathematics, here it is. You put it into mathematics, then mathematics tells you these are the formulas that those particles, how they travel from A to B, should behave as. Do you remember these particles? These formulas. I asked you to make a snapshot of this from your memory, right? These are Maxwell's equations. So when people figured this out, this is a few decades ago in the 1950s, 60s, so on and so forth, all of a sudden they understood that not just how electromagnetism worked, it was really because of the symmetry of quantum mechanics, the rotating of the waves, the quantum mechanical waves of the particles, that needs to be sent to the other side because it cannot do it in 0 seconds. And the formulas are exactly what people figured out already 100 years before, right here, amongst other places, at the Royal Institution. So, going back to our question, can you build a universe without this? And the answer is no. Light, photons, electromagnetism is there because nature is extremely vain. She loves her symmetries, but at the same time must also adhere to this speed limit that it has. So what are photons? What is light? Light is nature's way of being symmetric and making sure that the symmetry gets transported all of the universe without ever breaking the speed limit. So as long as you have those two rules, you cannot build a universe without anything that resembles light. And we're extremely lucky because of that light, the existence of this phenomena allows us to study the universe, it allows us to look at each other and have this very beautiful discussion with each other tonight. Thank you very much.